Section 11.5, we're now looking at the cosine rule. We did the sine rule in our last section, so now we're just doing the cosine rule. This one is also in your formula packet, so good news there, you don't have to memorize this one. This is the way you would have seen it in the past back in geometry, is in this version here. This is the best format for when you are solving for a side length, but when you are solving for an angle, better if we reformat it like this to isolate the angle. So same formula, but this is just better formatted for finding an angle. Just a reminder on this, when you are solving for an angle, that does mean in the very last step you'll be doing the inverse cosine of whatever all this is in order to get that angle. So that would be our last step when you're solving for an angle. So the sine rule, remember, was best used whenever you knew an angle and the side across from it. And that's when we could use the sine rule. The cosine rule, it still works in every case, but it's still better in some cases than others. So for example, in this case here, in a problem on a test, we would always check to see if the sine rule is available first. But you'll notice this is the only angle that we know, and we do not know the side across from it. So the sine rule is out for this one, and so we fall back on the cosine rule. Main idea for the cosine rule is to understand that this lowercase c goes hand in hand with this uppercase c. So whatever angle this is that you're going to work with in the formula, this has to be the side across from it. And so those guys always go together, which would make A and B simply the other two sides, or you could say the two sides that formed this angle. So if I'm looking at this one right here, so obviously this will be the angle that I'm working with. So let's just call that angle C. That would make this side C, which is where you're getting the x squared right here, which make the other two sides A and B. So the two sides that form the angle are what we would call A and B. But it's just pretty much a direct plug into the formula. Nothing too fancy about that one, just plug in the stuff. You do got to make sure that you put it into the calculator right. That is a common problem, so do be careful, but give one a try just to make sure that you're doing it right. But that's how it would look. That's how it would look in the calculator when you isolate x. And this is what we get to 3 sig figs. Looking at another case right here. So this is a case where you are now solving for an angle. Again, notice that you can't use the sine rule here because you do not know an angle and the side across from it. So we go into the cosine rule. So here's what that other format for the cosine rule looked like. If we kind of isolate for the angle that we're solving for. If you stick with the original format, this is what the setup would look like. So notice that this is the side across from the angle that we are solving for. These would be the two sides that form the angle. And so that's all of it. We just have to isolate the cosine theta so that we can do an inverse cosine to get our angle. And so that's how that would play out to 3 sig figs. And again, really common that people just make mistakes in their calculator. There's a lot going on here, so be careful on that. So number 3 is a case where, just to show you, you can use the cosine rule even on a case like this, but really why would you? Because the sine rule is available. If we know an angle and the side across from it, this is a candidate for the sine rule, and that's what I would use given the choice here. But just to show you, you can use the cosine rule even in a case like this. Notice the problem that it creates is you have x's in 2 different locations, and so it creates this like quadratic formula scenario that you'd had to use on this in order to work it out with the cosine rule. And that's why it really wouldn't make sense to use cosine rule in a case like this. We would just stick with that sine rule. And then one more look right here at number 4. This is really a review problem on the SSA case. So again, notice we're dealing with a side angle scenario here. And so we do have enough info to use the law of sines. And so that's what was done right here for the law of sines. If we work that out, you'll notice that theta is 29.7. Because it's a side-side angle scenario, we're going to consider the other possibility here for the angle and say, okay, well, if that's 29.7, that would be the acute form of the angle. If I want the obtuse option for the side-side angle case, then I got to subtract my 29.7 from 180 to see what it would look like in the obtuse form. And so that's what you're seeing right here. So if we subtract from 180, this could be the other possible scenario for this SSA case. But if you just notice the numbers, if that's 150.3, and I already know that's 71.8, already I'm over 180. So the other possible scenario here for side-side angle wouldn't make sense. Not to mention, remember we have the other rule where because this side is bigger than this side, the angle across from 9.2, which is this one, must be bigger than the angle across from 4.8, which is this one. And so that rule also would tell me that the other option is out. All right, so you get a bearing problem in this one. So the difference now compared to the other bearing problem that we did earlier this chapter is we're now dealing with non-right triangles. So here's a bearing scenario with a non-right triangle. One thing I would encourage you to do on this one is, before going through with the rest of the video, see if you can try to draw this one on your own. It's pretty similar to the bearing problem that we did earlier this chapter. It's just not a right triangle. So I would encourage you to try giving this one a draw. That's the hardest part on these. Once you get the sketch laid out, the math is easy. It becomes like every other problem that we just did earlier on in the notes. So see if you can give this one a sketch. But here we go. We have a ship leaving the harbor. It's going to sail a distance of 40 kilometers on a bearing of 290. So let's just start with that for a minute. Remember that this would mean clockwise from the north. So wherever I'm going to put my pencil down to begin with here, so we're going to call this point H. This is the harbor. This is where we started. If we're going on a bearing of 290 from the north, that means I'm starting right here, and I'm going to go 290 degrees to right there. And so this line right here should have gone all the way through to the north, but that creates a total of 290. The way you would estimate that in your head is, remember, this would be 90 degrees. This would be 180. A 3/4 turn is 270. And so if this is 270, then we're going to go just another 20 degrees to create this line here. And so we can label that a distance of 40. Notice where we're getting the 70 right there. This is one complete circle right here. So if we went 290 already, this would be the remaining 70 degrees within that 360 rotation. Second step, from there, so the point that we are now at, we're going to travel 60 kilometers on a bearing of 42 degrees from the north. So 60 kilometers from 42 degrees. So again, this is the point we are now at. You always draw your northern ray, and right there we're going to go ballpark about 42 degrees from the north. And if the line from H to X was 40, and this one is 60, then I'm going to try my best to estimate about how long 60 would be in relation to the 40 that we already have. And so I want to try to go about 1.5 times the length of the line that we already have, and we're going to call that 60. And so that's what we have so far. Now a couple of questions that they're going to ask. Before we even look at those, let's look at a couple obvious points that we need to come up with here. So we threw in the 60, we got the 40. Remember that if this is 70, then that would make this guy 70, because again, this line would be parallel to this line. And if those lines are parallel, that makes this and this alternate interior angles. So they are both 70 degrees. We already knew this was 42. So we can finish off this 180 right here. That's a straight line, so that's 180. So if we subtract the 42 and the 70 from 180, that gives me this missing angle right here. So we know that's 68, we know that's 70. Let's see if we can finish off a couple things here. So now they're asking us in part B. So we have the sketch. Part B says, what is the distance that is final position from the harbor? And then part C, they're going to ask us for the angle of the bearing. And so we'll start with the distance here for its final position, point P. So we're finding this distance right here from the harbor, where we're at now for point P. So again, that would just be, making use of law of sines or law of cosines, whichever would be appropriate for the scenario. In this case, we don't really have the complete ratio for the law of sines, so I'd be using the law of cosines on this one. So that's what you're going to see in the work down below. So here's we'll call this angle C. So that would make this side C to match up with the formula up above. And so if we throw in the numbers into our law of cosines, then we can solve for that distance right there, and we get our 58.3 to 3 sig figs. And then the last one, they were asking for the bearing. And this one could be a little tough to see, but recognize that it says find the bearing of the final position from the harbor. And so that's kind of the relationship that we have to look at here. So if I'm looking at that point P from the harbor, so if I were to say, okay, well, here's north from the harbor, at what angle would I have to travel to get to point P? That would be this bearing right here. And so that's what we're trying to solve for, is that little piece right there. That would give me the bearing from the harbor to the ship's final position. And so looking at that, if we were to use our law of sines, and so here's the work that you can see for that. So if we use the law of sines, we can solve for the full angle for PHX. Let me show you how that would look. So we're solving for the entire angle right here within our triangle. And then if we subtract out that 70, that's going to leave us with this little guy that we want, which is our bearing to point P. And so that's the work that you're going to see here down below. So we use that law of sines to solve for PHX. So 72.51 degrees or 72.5 degrees was the entire angle. And then if we subtract out 70 from that, we get our 2.51 degrees. Notice that we didn't round to 3 sig figs until the very end of the problem. That's important. So that's why you didn't do 72.50 yet. You wait till the end of the problem to make sure you get a good 3 sig fig answer on that.